Alright, in this video we're going to talk about special logarithms. Right, so if you recall, and hopefully you watched some of the other videos that I've done on logarithms, a couple important things about logarithms. One, the base of a logarithm can be any positive number other than 1. Right, so there are an infinite number of logarithms that we could have, because the base of that logarithm could be any positive number besides 1, and there are an infinite number of positive numbers other than 1. Right, so we have an infinite number of possible logarithms that we could have. The other important thing to remember is that logarithms and exponentials are inverses of each other, right? And that'll explain why the two special logarithms that we have, right? So there's two logarithms out of all those infinite number of possible logarithms that we can have with the possible bases. Two of those bases are used so often that those logarithms get their own special names and their own special notations, right? And the first one of those is what we call the common logarithm. Right, the common logarithm is the logarithm that has base 10. Now, why is base 10 a special logarithm? Well, that's because our entire number system that we used is based on powers of 10. Right? If you think about place value, when you're writing out numbers, 1, 10, 100, 1,000, a million, a billion, those are all powers of 10. Right? Our decimal system, the place values of the decimal systems are the tenths, the hundredths, the thousandths. Those are negative powers of 10. Right, so our entire numerical system is based on powers of 10, and since logarithms are inverses of exponential expressions, well, our whole number system is based on exponents of 10, so the inverse of that, the logarithm with a base of 10, is a pretty important logarithm, and it's one that comes up all the time, right, because when dealing with our number system, everything's base 10. So, the special notation that we use for the common logarithm is we just write that log there, and we don't put a little base number there, right? This x should be more like up here, right? So log x without any number in the subscript, that means the common logarithm with base 10, right? We don't usually write it with the base 10 there. You can, but generally that's seen as unnecessary and not that cool in terms of like mathematicians who, they're pretty judgmental about what's cool and what's not. So if a mathematician sees you write log base 10 like this, they're going to say, oh, this person's not that cool, right? So write it like this, log x, right? So when you have that log there without that subscript, that's base 10, and it means the common logarithm with base 10, right? So don't write it like this. Write it as just log x. Now the important thing is, when you're doing a problem or reading a formula or something and you see log of x and it's missing that number in the subscript, you need to recognize when you see that, oh, this is the common logarithm, that's a base 10. Right? Because if you totally miss that it's base 10, you're like, well, there's no number there, so what am I supposed to use? Like a 1? No, it's 10, so use the 10. Right? So that's our common logarithm, base 10. The notation is just log of x without that subscript. Right? The other important logarithm that we have is what we call the natural logarithm. The natural logarithm is the logarithm with base e. Now, if you didn't see the video that I did about the number e and the exponential function with base e, why not? First of all, you should watch that video because it's awesome. But more importantly, the base e, the exponential function with base e, is used to model a lot of real-life situations like population growth and compound interest and radioactive decay and other things as well. Since the exponential function with base e is used so often in modeling real life, natural phenomenon, well, the logarithm with base e, since the logarithms are inverses of exponential functions, that means that the logarithm with base e gets used a lot. Right, and some of the stuff that we'll be doing in logarithms and some of the other videos that I'll be making, we'll be using the logarithm with base e all the time to solve different types of problems. So it's used so often that rather than write it as log base e of x like this, it gets its own special notation, which is ln of x. Right, so never write log base e of x. If you have a logarithm with base e, it's written as ln x. Right, ln for logarithm natural. I think a French person came up with it, so it's kind of backwards as far as the noun and the verb, the adjective. I'm a mathematician, obviously, not a language person. But ln for natural logarithm, ln of x. So again, the important thing is when you see ln x, you need to identify, oh, ln, that means it's a logarithm that has base e. Right, and e is that special number, if you recall from that other video I did, it's approximately 2.718. Right, it's an irrational number, and if you don't recall that or if you didn't watch that video, check out the video that I did about the number e and the exponential function e to the x. I think I did 2 videos on those. So check that out, but that's one of the important logarithms because, again, that exponential function e to the x power is used to model a lot of real-life phenomenon. And so when we're solving problems that involve that exponential function, we have to use the logarithm with base e fairly often in order to solve them. Right? So ln of x, logarithm with base e, log of x without that subscript is base 10. Right? So the two important logarithms, the two special ones that get their own special designation, their own special names, you need to know what those are. I wanted to show you on the calculator if you need to, and you probably will need to if you're studying logarithms. At some point, you're going to have to calculate logarithms. And to calculate logarithms, generally, we use calculators to do that, to show you where those buttons are on the calculator. So the log button for the common log, if you see on my, my TI-84 calculator, over here next to the 7, there's a button that says log, right? That's log base 10. So if I want to find the log of 80, let's say, I just hit that log button, type in 80, and I get 1 point, whatever that is, 903. Right? That means if I do 10 to the 1.903 power, it's going to equal 80. Right? So that's my logarithm with base 10. The natural logarithm is right below that on my calculator. Right? So there's the log button, and right below that is the ln button. So I want to find the natural log of 80. I do ln, I type in 80, I hit enter. That's 4 point, whatever that is, 4.382. So what that means is if I do e to the 4.382 power, that's going to equal 80. All right, so again, the common log, the natural log, your calculator, if you have a scientific calculator or a graphing calculator, it will have those buttons on there somewhere. It will have a log base 10 button, the common log, and it will have a log base e, the natural log button. Every scientific and graphing calculator has those on there. They might be in different spots if you have a different type of calculator, but you should be able to find those and use them when you need to. One other thing I want to point out on my calculator here, right, the ln button, if you look above the ln button, that's that e to the x button, right? ln is the logarithm with base e, and it shares the button with the e to the x. Right? Look at the log button. Above the log button, it says 10 to the x power. Right? So if you forget which one of those is which, if you have a calculator like mine, it blatantly tells you on those buttons, hey, the ln, that's the one that goes with e. The log, that's the one that goes with the base 10. All right, so it's right on there. They share those same buttons because the people who design the calculators are not stupid. They know that the ln and the e to the x are inverse functions of each other, so they have them share the same button. Right? The log and the 10 to the x are inverses of each other, so they have those two share the same button as well. All right, so, and if you watch more videos that I'll do, at some point we'll probably do an example where we have to use those buttons. So, if you keep watching my videos, you should see, those buttons in action. There's not that much action involved. It's just a finger pressing a button, but you get the idea. So what I'm going to do here is pause this recording and then put up an example problem that uses, I believe, the common logarithm in the example in a real-life situation. All right, so the example we got up here is one that involves the decibel scale, which, if you're not familiar with that, it's a scale we use to measure how loud something is. And before we even get into the problem itself, there are a couple other scales that you're probably familiar with just from everyday life that also use a logarithmic scale. Like you can see that the formula here for calculating the loudness of a sound in decibels involves a logarithm. Right? A couple other things that also involve logarithms. One of them is the pH scale that measures like how acidic or how basic a function is, or not a function, a substance is. Right? So measuring the acidity of a substance. So the pH scale is also a logarithmic scale, just like the decibel scale here is. And another one that most people are familiar with is the Richter scale that they use to measure how powerful an earthquake is. Right? That Richter scale also has a similar formula to this based on logarithms. Right? So there are a couple things in everyday life. Maybe not everyday life, like you don't hear about earthquakes every single day, but things that are pretty commonly known about that use logarithms, and most people don't realize that they're based on logarithms, right? But the decibel scale for how loud something is, the Richter scale, the pH scale, all use logarithms. Okay, so this particular problem. The perception of loudness B, measured in decibels dB, of a sound with physical intensity I in W per m squared, which is watts per meter squared, maybe, is given by B equals 10 times log of I over I sub 0, where I sub 0 is the intensity of a barely audible sound. All right, so basically how this works is a barely audible sound. Well, first of all, sound, if you're not familiar with how sound works, there's a vibration in the air, like there's like a wave of vibration in the air, and that tingles your ear, and then you hear that as sound, right? So the I sub 0 would be that physical intensity, the size of that vibration that you can just barely hear. Right? That's like our baseline. That's like the quietest thing that we can possibly hear. That's I sub 0. And we compare all other sounds to that one. Right? So I sub 0 is the intensity, the vibrations of that sound you can just barely hear, and then the I is the intensity of the other sounds that you're hearing. Right? And then this logarithmic scale, we're comparing the I to that barely audible sound, the I sub 0, and then that's giving us the decibel level of the sounds that we're hearing. All right, so I sub 0 is the intensity of a barely audible sound. We are asked to find the decibel level, or the loudness, of a sound whose physical intensity is 100 times I sub 0. All right, so again, if I sub 0 is that really small little vibration that you can just barely hear, if you have something 100 times as powerful as that, well, how loud is that sound? What is the decibel level of that sound? All right, so that's what we need to figure out here. And one of the reasons I hate word problems, probably different reasons from why most of you hate word problems, not because I think they're hard to figure out, it's just they take up so much space to write them down. Like I had to pause this for like 5 minutes to write all this stuff up here, and now to even solve the problem, I just have to erase all this stuff. Right, so the most important thing is I'm obviously going to leave that formula up here, and then the stuff at the end that tells us what we're actually trying to do. All right. So the physical intensity is 100 times I sub 0. So really just that little stuff at the end is all we really need to solve this problem. All right, so my I, right, the physical intensity of the sound that I'm interested in, right, the intensity of that sound I is 100 times I sub 0. So I is equal to 100 times I sub 0. All right, pretty basic. So that's what this down here was saying. So we got that now. And now we want to figure out the B, the loudness or the decibel level of this sound that we're hearing that's 100 times that threshold of what we can barely hear. All right, well, let me take I equals 100 I sub 0 and plug that into this formula here for I. So B equals 10 times log of 100 times I sub 0 over I sub 0. All right, so I plug in what I is equal to in place of the I, and now can I simplify this? These I sub 0s here, am I allowed to cancel those out at this point, or am I not allowed to? Well, for this one, since it's 100 times I sub 0, since there's multiplication there, I am allowed to cancel those out. If this was 100 plus I sub 0, I can't cancel those out. All right, but since it's multiplying, I can. So I get B is equal to 10 times log of 100. All right, so now I can do this calculation, right? I can do 10 times log of 100 and see what the decibel level is for this sound. Now, log of 100, right? There's no subscript on this logarithm, which means it's one of those special logarithms that we just talked about a few minutes ago, right? The one that has the word log without a subscript, remember, that's the common logarithm, which is base 10. All right, so looking at this, and if you've seen some of the other videos I did about logarithms and you remember how to evaluate a logarithm, some of you may be able to look at this right now and say, oh, I know what log of 100 is, right? Because it's 10 raised to some power to make it equal 100. So what power do you have to raise 10 to equal 100? Well, that's 2, right? So this equals 10 times 2, which equals 20 decibels. Right? So that sound that's 100 times more intense than the most barely audible sound has a decibel level of 20 decibels, which I'm pretty sure 20 decibels is still a pretty quiet sound, right? Loud, things that are like pretty loud are like near 100 decibels, I think, maybe a little bit more than 100 decibels for things that are like really loud. So 20 decibels is not too loud. Right now, this log of 100, if you looked at that and like you didn't understand what I just did, number one, go back and watch the videos that I did about logarithms and evaluating logarithms, because it's really not that hard to figure out. But if you can't figure it out, right, if you just go to your calculator, the log button, right, the one over here for the common log, and then type in 100, and log of 100 equals 2. Right, so again, when you have the common logarithm, right, the one that's base 10, your calculator has a button for that. So you just hit that log button, type in whatever number is here, and then you do 10 times 2, you get 20. All right, so that's an example problem that involves the common logarithm. And like I said, the common logarithm, since our number system is based on 10, it's all powers of 10, the common logarithm comes up kind of a lot. So does the natural logarithm, as we'll see in some of the other videos that I'll make and some of the other examples that we'll do. We'll be using that natural logarithm quite a bit as well. All right, so make sure you check out all these other videos I'm doing on logarithms.